All right, good morning. Welcome to Attacking Electric Motors for Fun and Profit. We're in Islander FG, if that's where your destination was taking you. And today we've got Matt Jablonski presenting. A couple of brief notes. Stop by the business hall in Mandalay Bay, Oceanside, Shoreline Ballrooms on level 2 during the day. Welcome reception tonight is at 5:30. Black Hat Arsenal is in the business hall on level 2. And join us for the Pony Awards in Lagoon G, H, and I at 6:30 tonight. With that, I give you Matt Jablonski.
Hello, Black Hat. I hope everybody here is enjoying Black Hat so far. If you want to learn about attacking movement and robots, drones, or other systems that use electric motors, like critical infrastructure, you're in the right place. And as Bill said, I'm Matt Jablonski, and this is Attacking Motors for Fun and Profit. I'm a PhD student at George Mason University, and I work in the Radar and Radio Engineering Lab under Dr. Duminda Wijesekera. We've been studying SCADA systems specifically with regards to railroad systems, and we noticed over the last few years that there are a lot of overlaps between the attack surface in these systems and other systems such as drones and things that use electric motors. So that kind of brings us to our talk here today. So in this work, we simplify the attack strategies that, against electric motor systems and show how they can be universally applicable to non-SCADA moving systems such as robots, drones, or other systems that use electric motors. We present the motor threat model, which basically simplifies the description of an attacker and how they can disrupt or control movement in these target systems. To learn what not to do with electric motors, we conducted many experiments in our lab environment, and we overheated and burned out and caused lots of fires. And so despite what you might see here, we recommend always following security warnings, or safety warnings, excuse me. So as a quick overview, we will discuss the safety and security of moving things, the motor threat model, various motor attack methods at each layer of the threat model, as well as experimental validation of our model, and conclude with some discussion. In order to describe the motor threat model, we'll introduce a game for you guys to play along with. So imagine most attendees here at Black Hat know something about security and threat modeling, and I hope you can play along. This game is basically structured to help understand how to threat model movement. Your company, in this case, was hired to assess the security risks of a proprietary drone system designed to deliver packages worldwide. Hundreds of operators around the globe will manage 30+ different drone models that are proprietary, ranging in size, to deliver packages to cities around the globe. And they obviously have physical and remote access to these drones. The operating company decided they're not going to do background checks for these personnel. So control will be wireless, within the line of sight, or over the internet, and will be automated to every possible extent. So what is the attack surface? What are the threats? And if you have ever worked for a pen testing company, we need your report today. In any critical infrastructure system, safety has historically been the priority. Safety controls focus on avoiding accidental risks. On the security side, we focus on intentional misuse. So intent is the key difference between safety and security, really. For safety, operators in our drone system will be trained and certified to handle the systems as they would for the real world environment. The systems are built to have fail-safes, so when some unexpected event occurs, protections will be in place. Generally, regulations and standards have been developed over years for these systems that move, and different organizations have oversight depending on the system. In the example of drones, it'll be the FAA in the United States. Security risks, on the other hand, are traditionally different for every system. So here's our first security problem. As InfoSec professionals, we think like bad guys. And then we immediately consider all the potential methods to misuse this system. Within our example scenario, maybe this meme here is the first thing that comes to mind. But identifying threats and mitigations is where the fun and profit part of our talk comes into play. Sometimes this approach is very structured, and we can fall back on our training. For example, if targeting a web application, I know I can use burp to find cross-site scripting or CSRF vulnerabilities. Other times, we're forced to reverse engineer the system and logically show where the risk could occur. So recommendations such as, this is a terrible, horrible, no good, very bad delivery drone thing that you're delivering is not going to lead to fun and profit. So let's look inside the system. What do we see? We immediately, what comes to our eye is there are two communication channels. One is 4G LTE over the internet, and second one is a 2.4 gigahertz channel for line of sight control. There's a couple of different possible operator interfaces then, depending on which interface they're communicating with. And this system has a number of sensors to include GPS, accelerometers, other inertial measurements, etc. And it has a central controller that manages, or that maintains, excuse me, wireless communications and controls the electronic speed controllers, or ESCs, used to control the motor. And this controller is running Linux. So maybe some thoughts are coming to mind about what you could attack here. At this point, we'll probably take our research and start looking through other drone attack talks in recent years. And we'll find examples in research about reverse engineering communication channels, uploading flight plans via FTP because somebody thinks that's a good idea, or taking over the drone's Wi-Fi hotspot and using a phone app to control the drone. These are all good things to get started. However, the vulnerabilities are always system specific, and remember that our scenario is a proprietary system. So let's take a step back. Having reviewed related systems, you may want to go over how do electric motors work in the first place. So in digital systems, every electric motor is connected to a drive, which provides some electric power to the motor. These drives can be electronic speed controllers, as I mentioned, or in SCADA systems, they're variable speed drives, or variable frequency drives. They can be embedded or even a microchip, or part of a SoC. Some drives have more than one motor. It just depends on the system. Pulse width modulation allows for varying the speed of the motor, and in order for pulse width modulation to work, it fluctuates the voltage, and when voltage is greater than 0, the motor pulls current in order to move. The frequency of switching is controlled by a clock, and the amount of time where voltage is greater than 0 is known as the duty cycle. Both the clock and the duty cycle are controlled in hardware and software. Electrical current provided by the drive is the input to the motor. At a high level, the current flows through windings internal to the motor and interacts with the magnets to produce an electromagnetic field. The rotor is part of the motor that moves, the stator is the part that's stationary. That's kind of self-explanatory. The output of the motor is mechanical energy in the form of torque and speed and output power, physics stuff. The structure and behavior of the motor can vary depending on the type of system. It can be DC versus AC, or rotary versus linear, etc. And the selection of the motor is really based on the load. So all motors basically have data sheets. So if you're reverse engineering or targeting a system like a drone, look up the data sheet for the motor. It'll tell you about the torque versus speed relationship, and which tells you the operational parameters of the drone. In this case, for this simple graph for a brushed DC motor, if you look at the far left, when torque is high and speed is 0, basically, this is known as a stall torque, and prolonged exposure to this kind of behavior will overheat and burn out the motor. When speed is high and torque is 0, this is a no-load condition. And basically, in either the stall torque or no-load condition, power output is minimalized, as you can tell by the right graph. So how do we design a control system to drive a motor? It's basic control theory, of course. There are two types of universal design methodologies to build such a system: an open loop and a closed loop design. In an open loop design, some input is provided to a controller without changing the system state. The controller executes the input, passes commands to the drive, and provides current to the motor, impacting the output load. In closed loop, we had a feedback mechanism, which sensors collect data on the current system state to the environment. The controller uses this information to adjust the drive and motor parameters. And that's basically it. However, this brings us to a big security problem. Understanding generically how movement is controlled and using control theory tends to be bring more, what ifs and questions. Where can an attack against movement come from? What would the attacker's goals be? How realistic are security concerns at each level of the stack? Another concern is that digital control commands through pulse width modulation are not authenticated. Controller or drive controller access would allow for modifications to a motor's duty cycle, resulting in timing attacks with real-world consequences. This is the challenge of basically managing continuous movement using discrete commands. So since we took a step back and looked at electric motors and focused on digital control systems for movement, we might start researching other systems and their threats and vulnerabilities, looking for attacks on movement. Research and security focused on robotics, SCADA systems, printers, 3D printers, and other moving devices show a lot of parallels to our drone or proprietary drone system, as they all use a controller to create precise movements using electric motors. However, we found there's not a universal or common threat model to describe these relationships, despite the common design patterns. So that's our goal for this talk, is to present one. So let's step away from drones and look at some common attack strategies and requirements. Some of our requirements are attacks using digital movement controls have real-world impacts, which we want to identify. Attacks can be either cyber or physical in nature. The model should identify where attacks that leverage discrete commands may occur. There's basically two different models that we can use as a starting point to threat model movement. The first one is the ICS cyber kill chain, which defines SCADA attacks as requiring two different stages. Stage one covers cyber espionage, but it's really just relevant to SCADA systems. Stage two is probably more applicable to movement in general, but it's kind of vague, as shown in the picture on the right, if you can see. Develop, test, deliver, modify, execute, attack. It's pretty vague. The ICS cyber kill chain does define goals for movement, which we can use in our threat model. There are three goals, basically. An attacker will want to control the system, disrupt the system, or steal data regarding the system. We'll expand on these in a moment. The second possible model that we can look at is MITRE's ICS attack framework, but it's still in draft, and it's also just focused on SCADA systems, not drones or robots or anything else. It allows for identification of attack stages that allow for attack attribution as kind of a post-mortem analysis, but they don't focus on physical attacks, and the model cannot be applied to all systems. So with these measurements in mind, and after an extensive review of our electric motor systems and throwing a dash of control theory, you're welcome, we came up with this model, which we call the motor threat model. This looks complex and hard to remember. Don't worry, we'll simplify it in a moment. So just like with control theory, controls flow from 7, operator, to 5, control, to 4, drive, to 2, motor, to 1, load. The digital control portions require 3, power, as input, which may be single or three-phase power, even batteries, depending on the system. Finally, in a closed-loop system, 6 sensors collect data and provide that feedback information to the various layers in order to make precise movements, decisions based on the hardware and software design. Okay, let's see how we can make this simpler. So if we take the layers and stack them similarly to an OSI stack or a file system stack, we can more easily categorize attacks against movement. The stack from top to bottom is 7 operator, 6 sensor, 5 control, 4 drive, 3 power, 2 motor, 1 load. If you notice from the drawing, starting at the right, physical attacks can really occur at any of the layers and are limited to basically stopping or stealing movement. Controls at all layers. Similarly, on the left, cyber attacks are more effective at the higher layers. Traditionally in research, whether it's drones, robots, or SCADA systems, attackers have targeted the operator, sensor, and control layers because this is a natural attack surface for network and cyber-related attacks. However, depending on the system, the drive, power, and motor layers may require firmware or even have network controls. We simply star these layers to show that most cyber attacks will target the higher layers. With this description, If an adversary targets the lower layers, they basically disrupt or take control of movement from the higher layers. This may be enough in many cases for an adversary to complete their mission. We believe the stacked approach simplifies differentiating between cyber and physical attacks too. And we'll show you that throughout the rest of this talk. A friend of mine recommended coming up with a simple mnemonic method to memorize the layers. The best I could come up with was offensive security, can do, precise movement, lulls. Yeah, sorry. As previously mentioned, there's really 3 high-level attack objectives for movement that the stacked model can assist with identifying kill chains to prevent. Understanding the adversary's goals before identifying attack strategies is critical for defending any system. So control, as mentioned before, with this objective, the adversary wants to steal control to basically achieve some goal, which is refined based on the system. Generally, this is done at the higher layers through cyber attacks, but physical access may be possible to the operator interface at the operator layer. This is basically easiest at the operator, sensor, control, or drive layers. Disrupt. With this objective, the adversary may want to stop movement or inject commands to modify precisely timed movements or prevent operational controls. This can be achieved through both cyber and physical attacks and is achievable really at all 7 layers. And then finally, data exfiltration or just simply steal data. With this objective, adversary may want to violate IP or privacy of the system's owner to track the system usage. This is generally done through cyber attacks and is easiest at the operator, sensor, or control layers. So now that you have some kind of idea of the types of attacks and the desired attacker outcomes, we provide this table to basically show these relationships at the various layers as shown at the various layers. On the right 2 columns, you can see how and where cyber and physical attacks could be used at each of the layers, as well as we've identified the attack objectives that could be leveraged at each layer, whether it's control, disrupt, or data exfiltration. The operator layer is basically unprivileged motor control. You only can use the APIs that were provided to the operator layer for moving the system. And it consists of attacks targeting either the operator interface itself or the operator control channel. Lateral movement to the control layer is possible through this channel. The sensor layer provides feedback on the physical environment, and attacks against this layer are designed to basically falsify the data in order to trigger some different movement. It consists of 2 different levels, either targeting the sensors or a wireless sensor network if one exists, or even the out-of-band safety system, which provides fail-safe controls back to the controller as input. In the control layer, layer 5, it's basically privileged access or root control to movement in the system. If you control the system's controller and or the control drive channel, which is used to precisely control motor movements, you basically own own movement within the system. Below that, at the drive layer, it handles individual motor movements using some minimal configuration designed for the specific motor that drive was designed to control. This layer consists of attacks both on the drive controller and attacks on the drive motor channel, which is usually just the motor leads and where current flows from the drive's power supply. For the last 3 layers, these are primarily physical attacks. The power layer basically describes attacks targeting electrical power inputs to system components, which can limit or prevent movement altogether, obviously. This layer requires access to the power system and generally requires physical access, or a physical access attack is expected. The motor layer is why we're all here. All movement basically goes through the motor. Generally, these attacks require physical access, but some motors, such as digital servos, can be reprogrammed to completely change their movement outcomes, which we'll provide an example of in a moment. Finally, the load layer is the output layer. It consists of the motor shaft, connecting gears, and any components that interact with the physical world. An attack here requires physical access. So now with the 7 layers design, that's our 7-layer stack. The types of attacks at each layer really vary per system, We'll show how to further refine this model for attackers, defenders, and we'll get back to our game in a moment. But we've got a number of attack experiments to basically show at each layer some examples of how an attacker can control or disrupt movement. So for our first target, we just have a simple remote control car. And this is an attack basically against the operator control channel. It's modeled after really many attacks and research taking control of drones and robots using SDR. So here we see the remote control car and the operator interface. And the operator interface basically has two controls, forward and reverse. Wireless controls the vehicle over a standard communication channel at 27 megahertz. And a review of the controller shows that a simple oscillating crystal produces the resonating frequency for both forward and reverse. So with a hack RF1, all we need to do is capture both the forward and reverse controls for about a second, and we've got complete control of the vehicle. Because it's just an oscillating crystal, we don't even have to decode, we don't have to filter, we don't require any complex reverse engineering, we just are able to control movement. So we can slice up the collection files from the SDR and basically move the device any way we want. The picture on the left basically shows the wheel turning and the operator controller in the background because the SDR is controlling the vehicle. This second attack experiment was designed also to target the operator control channel, and we call this attack a remote pin control attack. We have a simple target system here designed to allow us to control a motor, inject attacks, and graph the resulting output of torque using a mini-pro dynamometer, or a dyno. In this experiment, the Pi is the controller, sending commands to the electronic speed controller using pulse width modulation through GPIO 18. The speed controller provides current from the LiPo battery to the brushed DC motor and is connected to the dyno for measurements. This physical setup will be used in many of the examples kind of moving forward, and I'll refer back to it. The Pi is running a baseline script that just runs the motor at a particular speed using the wiring Pi library. It's also running a PIGPIO daemon, which is built in a Raspbian for GPIO control. And we enabled remote GPIO, which basically, if you can interact with it over the network, you have direct memory access to the Raspberry Pi. PIGPIO, developers added this feature to simplify remote pin management for hobbyists, but we're going to exploit this feature. So assume we gain access to the same network as the Pi. Running Nmap on the network identifies two key features about the Pi. Basically, TCP port 22 shows that it's running a Raspbian version of OpenSSH, so we've identified a Pi. And TCP port 8888 is open with an interesting string. We've got NCP:DMDT. And we checked several different Pi versions and versions of Raspbian, and we believe this is an indicator for remote GPIO. So the script on the right is just a simple Python control script for the attacker that could be leveraged through their tunnel into the network or by importing the GPIO 0 Python module onto a compromised host in the local network. The attacker basically changes the clock value or motor.frequency to 250 and then alternates the duty cycle between 30 and 40%. For this example, we guess GPIO 18 is a pin we can do stuff with, although with this particular example, the attacker is really blind to the GPIO control on the Pi from the network. Just simply calling the script with PIGPIO _ ADDR environmental variable, targeting the target's IP address, triggers the GPIO 0 module to send the commands over the network to port 8888 and basically giving the attacker control over the pin. So here's an output speed graph from the dyno, just basically showing RPM versus time. The top line is the baseline run, and it's suspected motor behavior without the attacker's involvement. This script uses a single motor command to drive the motor up to about 24,000 RPM, as you can tell. We have a circle highlighted on the graph to show where the attacker's script basically takes control over the motor. The alternation of 30 to 40% can be seen in the variation of speed over time and kind of looks spiky. As a baseline script does not repeatedly issue discrete commands and there's no other sensors monitoring the system, the attacker now has complete control over movement from the operator control channel. So on to the sensor layer. Attacks at the sensor layer are a little more complex, generally require additional reverse engineering to take control of the system because it's critical to understand how this feedback data is used as input to affect movement decisions in software. In this setup, we have a ADXL 345 accelerometer, which in software, the PI is just taking the X, Y, and Z axis from the accelerometer and then using it to control the angle of the output servo, as you can see in the two drawings on the right. The accelerometer communicates the PI using I2C serial bus protocol. And the I2C protocol is a master-slave protocol, where the master requests data from the slave. In this case, the master is the PI, accelerator is the slave. To simplify this description, in the middle picture, the board is flat on the table, and we see that the servo is angled almost at like 6 o'clock because of the X, Y, and Z axis. And when we tilt the breadboard, we see the servo adjusted by the PI and the drive controller to an angle between about 7 and 8 o'clock. We can use a Saley logic analyzer to sniff, capture, and decode the I2C protocol. So when we decode, we observe the I2C handshake between the PI and the accelerometer. Takes place over 3 bytes, and then there's an additional 6 bytes of data providing the X, Y, and Z coordinates. We cheat in this example and connect an intact PI to the I2C bus to capture the I2C address of basically 0 by 53, targeting the ADXL 345. So then we can rewire the PI, as shown in the drawing on the right there, turning it into a I2C slave as an attempt to disrupt or control movement. So the pictures on this slide basically show the outcome of 2 different attacks. So on the left, this is a disruptor jam scenario. Our attack PI basically responds to I2C requests at the same time as the accelerometer. So the responses collide on the bus, but the input device interprets the bits anyways. And in our simple collision test, the board just moves the the servo angle in the manner to about 7 o'clock, as you can see in that left drawing. In the right picture, we basically sever, or we could desolder, if this wasn't on a breadboard, the ADXL 345, and because we can communicate and respond to our target PI, we have complete control over those 6 bytes and can basically move the servo to whatever angle we want. So that's an example for this sensor layer. Onto the control layer. Basically, here we assume the attacker has gained access to the controller of our PI in our previous setup using the ESC and brush motor and dyno. The PI is running a baseline script that increases the speed of the motor every half a second until it hits about 16,000 RPM at a peak, and then it sleeps for 5 seconds and then starts decreasing the speed every half a second. So the graphs on the left and right show 2 different attack strategies against this script. So in the graph on the right, the first circle on the left is basically a single command injection where the attacker is saying, hey, stop the motor. Because the controller is updating its frequency and speed every half a second, this is minimal effect, but kind of jerks the motor. However, if that same single command injection is applied after the motor sleeps for 5 seconds, you can see that the motor basically starts grinding to a halt until the controller wakes up and applies additional commands. In the second graph, it just basically shows a single command injection. Oh, I'm sorry. The graph on the right, the attacker begins basically issuing commands every 100 milliseconds from the first red circle through the second red circle at a faster rate than the motor controller software. And you can see that the motor, the attacker has complete control over the motor between these 2 circles, keeping a motor at about 10,000 RPM. So if you have more granular access and you issue commands at a faster rate than an application, this is just showing how you can take over the motor as an attacker. For a second control attack, this basically, we target here the control drive channel to take over user movement. So as a reminder, basically the PI uses pulse width modulation as a control signal to and from the electronic speed controller to basically drive the motor. In this setup, we show how to introduce a hardware implant to take over control of the channel and of system movement without the controller even knowing, and also assuming that sensors are not present. Generally, wiring in drives like in systems like robots or small moving vehicles, you'll see a 2-wire or a 3-wire connection, and the pinout is noted here in the slide. The black wire is a common ground wire. The red wire is basically designed to provide current, and it may or may not be used in the event a separate power rail is used. A white or yellow wire is used for control and is usually just pulse width modulation. So here we take an attack pi, which could really be any hardware implant, and we just connect the white wire there to GPIO 18, which is our pulse width modulation on our attack pi, and the black wire to the attack pi's ground. And then the attack pi, we have a simple script in Python where we set GPIO 18's pin mode to input. We wait about 5 seconds after seeing a pulse width modulation signal, and then we change the GPIO 18 pulse width modulation mode, and it basically takes control of the motor. This graph shows the results. The blue line represents a baseline run that drives the motor up to about 24,000 RPM. The 2 attack runs in this graph show our attack script takes complete control over the motor. We can slow down or speed up the motor at will and completely control the pulse width modulation signal. The hardware implant attack works once the attack pi takes control over the pin, basically. Smaller boards could be used to replicate this attack. A good mitigation here might be to make wiring harder to access within the system, maybe adding tamper evidence or tamper resistance controls to prevent attacks against this channel. Okay, so let's move on to the drive layer. Many times the drive layer is a separate controller or board from the main controller, as the drive controller is just designed to handle the additional power load in order to drive the motor. We continue our example here targeting the Pi, as open source examples are easy to follow. The Raspberry Pi 3 B+ uses the Broadcom BCM2837 SoC, and physical memory registers are used to control or change pin status within the SoC. The code here may be a bit hard to see, but we have more details in the paper. We're basically able to identify the register locations in memory through reading the data sheet and reverse engineering the wiring Pi library, which is a commonly used library for pin control in the Pi. Once we identify these locations, we can memory map and control pins by just updating their status in memory. For our first attack, we basically use the same Raspberry Pi setup that we did before. This attack is essentially the same attack presented by Abazi and Hashemi at Black Hat Europe 2016. It was called Ghost in the PLC. Basically, with root or similar access to the running application, an attacker can change the pin mode from pulse width modulation to input, which we did here. And you can see that once the pin was changed to input, it basically pulse width modulation stopped and the motor stopped as well. Hashemi and Abazi showed how to turn this into a rootkit. So for a second drive layer attack, we change our configuration to use a brushless motor, as pictured here. Brushless motors are more efficient than brushed motors and do not spark under abnormal conditions, and we had some issues with fire in doing this experiment. So we want to control abnormal conditions, basically to modify the clock and duty cycle values to see the impact on the motor. So the graph here basically shows the results of modifying the clock and data registers. In software libraries, to control the speed of the motor, the libraries may adjust the clock and duty cycle values to ensure that the motor runs at a certain speed, or in the case of a servo motor, at a certain angle. By keeping the range register static, we cycle through clock and data values to see what the impact of motor output would be. And as we increase the clock value, you can see that the data value needed to move the motor, basically clockwise or counterclockwise direction, decreased as frequency in the clock increased. An attack strategy here to disrupt performance against a motor could simply involve changing the clock value. which would change the direction of the motor or even stop the motor altogether if the application used duty cycle values that produce no movements with the new clock value. For our last attack against the drive layer, we take control of the ability to read and write those GPIO registers to basically record and play back movement to allow us to reverse engineer movement in a system. If we go back to our earlier Pi setup with the brush motor and run a script, we can write a script basically that captures the clock, data, and range register values every 100 milliseconds, or at least more granular than the controller application that's running. A second script can then just be run to play back these values every 100 milliseconds. And as we can see by the two curves in the graph, the capture and playback of movement by simply monitoring register values produce the exact same movement. So this technique, basically, as I said before, could be used to reverse engineer movements in complex applications, but it will generally require root access. So with the power layer and below, attacks usually require physical access. So techniques have been proven feasible in research, such as firmware attacks and rechargeable batteries that could be used to modify overcurrent or low voltage parameters. In this experiment, we simply show the results of introducing a low voltage battery to movement. A low voltage battery basically simulates a brownout condition on the motor's performance. We ran our LiPo battery down to a low voltage condition, which is usually not recommended because LiPo batteries can catch fire or supposedly explode in low voltage conditions, which we didn't actually see. But the baseline run in this graph shows the expected motor performance under normal voltage conditions, running the motor up to about 25,000 RPM. With the low voltage battery, the motor was slow to take off, and the battery also just popped and shook the workbench when we started the motor up. This graph shows the motor was unable to come close to its target RPM and just kind of topped out at about 18,000 RPM before petering off. This graph is those same two runs, but we compared torque and power output, which might be kind of hard to see, so we apologize, under the low voltage scenario. Basically, both torque and power output are drastically affected negatively without the proper voltage, just because the motor's struggling to pull current. And if the motor's struggling to pull current, it can overheat and reduce the lifetime of the motor. So next, we'll go on to the motor layer. Attacks against the motor layer are usually physical and could be as simple as pulling leads or shorting the motor if overload protections are not in place. We decided to be a little more creative and wanted to see the impact of an electromagnet on the performance of the motor if introduced to a running motor. We basically hypothesized that the additional electromagnetic presence within the motor would change the movement characteristics of the motor. And we procured a 500 Newton electromotor, as you see there, which runs off a 12-volt battery. We found that by placing the electromagnet over the holes used for ventilation in our brush motor actually did impact the magnetic flux internal to the motor, but not in the way that we had anticipated. So in this graph, we show a baseline script that runs the motor up to about 25,000 RPM again. And when the electromagnet is introduced to the motor in the second attack run, the same baseline script consistently increased the motor speed by about 3 to 4% up to 26,000 RPM. The circle in this graph is used to highlight the removal of the electromagnet in our second attack run. Once removed during the run, the motor basically slowed back down to the original intended 25,000 RPM target. So moving on to our second motor attack experiment, we wanted to show how simple it is to reprogram a digital servo if they're using a target application. If your target robot or drone or any kind of system has a digital servo, chances are it has some kind of marking, either externally or internally, that tells who that manufacturer is. If you know the manufacturer, you can generally find that they also like to sell programmers to change the characteristics of the motor. So the left picture, we basically show the high-tech programmer in line with the servo, along with some of the characteristics that can be reprogrammed, such as direction, speed, and dead bandwidth. In the right picture, we show how easy it is to change the servo's direction from clockwise to counterclockwise. This change is permanent, really, until somebody fixes the motor or until it's reprogrammed again. So basically, these pictures show the results of changing the direction. The top pictures, we have a motor changed in software to 25, 45, 90, and 125 degrees. And then we flipped the motor from running clockwise to counterclockwise, and we just ran the same script again, 25, 45, 90, 125 degrees. You can see that basically angular movement for the digital servo is reflected. So if this was done to something like a 3D printer or a robot, basically the movements would appear backward to what an expected output would be. The controller might detect the calibration or detect an issue during calibration, shut down, or the system may fall back to a fail-safe state. And for our last layer, the load layer, these attacks are almost always physical, and the attacker may want to prevent any movement or shift weight on the load to overheat the motor and reduce the motor's lifetime. Here we have a simple experiment to show what happens when we burn out a motor. We procured a simple desk fan, as shown in the picture, and used a temperature probe to monitor the motor's temperature over time. This fan uses a brushless motor. I set the fan basically on high setting and use my hand to prevent it from moving, and every 10 minutes allowed it to move freely and measured its speed with a tachometer to see the motor's performance over time. So what ended up happening was after 61 minutes, the fan burned out. Based on the graph on the right, you can see that it started off operating at about 7,000 RPM and dropped over that hour to about 6,000 RPM before completely dying. On the right graph, you can see that the temperature of the motor internally rose to 180 degrees. And so at prolonged high temperatures, what happens is the winding insulation in the motor lifetime, it significantly decreases until the point that the insulation cannot assure proper current flow and the motor just stops running. And this is actually another way to attack motors, just apply high heat really to the insulation. You'll just burn your motor out. Visually, if we compare a good motor and a bad motor, we don't even see any difference. And so forensically, it just looks like the motor wore out over time. Okay, and that concludes our example experiments at the various motor threat model layers. And hopefully now it's kind of easier to understand how attacks at different layers can result in disruption or control to an electric motor system's movements. So you see the 7 layers, and remember, offensive security, can do, precise, movement, lulls. So let's return back to where we started and complete our game. In case you forgot the scenario or showed up in the middle of the talk, here it is again. You're a risk assessor, and your company just landed a job of assessing a global drone delivery system. The drone company uses about 30 different drone models, hundreds of operators worldwide, have both physical and remote access, and the company won't be conducting background checks. And control occurs over the internet. So what can go wrong? Well, with any threat model, we want to define who our attackers may be. In this case, we consider the following actors may have interest in disrupting movement over a drone delivery system. Nation-state adversary is good at cyber and physical attacks. Such an attacker can target all 7 layers of the motor threat model. A cyber criminal is good at cyber attacks. They usually profit off of data collection and could target data in the drone system at the operator, sensor, or control layers. A terrorist is good at cyber attacks in the system in this scenario. They would be interested in controlling or disrupting movement to cause fear. These attacks could occur at the operator, sensor, or control layers. Finally, an insider could also leverage cyber or physical attacks, and they may either be a disgruntled employee or a social engineering victim. In the case of a disgruntled employee, they could sabotage movement at any layer. In the social engineering case, these attacks would just occur at the higher layers. The next step, we refine our 3 goals for a target system to allow us to create attack graphs and identify all the kill chains which we could use to build security mitigations and prevent or detect attacks. For the control attacks, the attacker may want to steal the drones or alter movement off their desired course. For disrupt attacks, the attacker may be interested in creating physical damage or physical harm, or just preventing movement altogether. For data exfiltration attacks, the attacker may be interested in gathering data with regards to systems usage or deliveries, which could be considered a privacy invasion. So with the motor threat model, we can now basically create attack trees for all three attack graphs, or all three attack goals, excuse me. For each goal, we know the layer at which it'll occur. We can identify the necessary components and channels that may make up each layer, review the hardware, software, and communication protocols, and create detailed attack graphs which could be followed at each layer to reach the same goal. The result of these graphs is a multi-layered kill chain, essentially for movement, which can be used to secure the system's movements. If we know where the cyber-physical attacks could occur, then we can prevent those attacks from occurring as security professionals and gain fun and profit. So now to close out our game scenario, we just revisit the internals of the system, and we can begin applying labels to the components according to the motor threat model layers. So each component can be studied individually by a risk assessor to produce those attack trees that I just showed you against control, disrupt, and data exfiltration objectives. We've analyzed this approach against several systems, to include SCADA systems and drones, obviously, and robots, and found that it works for systems that we've analyzed that use electric motors for movement. More complex systems will result in obviously more complex models. However, the threat assessment could be conducted in stages, maybe following individual layers depending on where the attacker model looks like and their possible goals. So before I close out, here's my boneyard from experimentation. I burned out a lot of motors, caught a lot of things on fire, and probably most of it was due because I'm pretty crappy solderer. So as for Black Hat soundbites, there's 3 takeaways from today's presentation. You can identify basically 3 attack goals against movement in electric motor systems: control, disrupt, data exfiltration. Any system that leverages electric motors built using control theory, basically has 7 layers that can be attacked from either a physical or a cyber perspective. And those 7 layers are operator, sensor, control, drive, power, motor, and load, or offensive security can do precise movement lulls. This works as a universal model against movement as best we can tell. And again, I mentioned that we've tried it against some of these other systems. So we hope that you find the motor threat model simple, and maybe it can even help us make it better. So thanks. This concludes attacking electric motors for fun and profit. I hope the motor threat model is easy to understand, and we're interested in feedback, and hopefully you'll provide reviews. And I'm happy to entertain questions or answer questions outside if there are any. Otherwise, we're done.